Welcome to this explainer. Okay, so we're going to dive right into something that completely shattered the illusion of how I thought reading actually worked. We read every single day, right? Often for hours on end, scrolling on our phones, reading books, checking emails. But the actual mechanics of how our brain and eyes process that text, it is completely invisible to us. It's not just seeing words and magically understanding them. It's actually this massive, highly complex intersection of language processing, visual acuity, and literally rapid-fire motor control. Right now, as you're looking at this screen, try paying close attention to your eyes. Just kind of feel how they're scanning the words. If I asked you to describe it, you'd probably say they're gliding smoothly from left to right, sweeping across the text like a continuous, smooth video camera pan. But what if I told you that impression is entirely 100% false? The human visual system is just an absolute marvel. Think about this. We make a staggering 250,000 eye movements every single day. That's enough to boggle the mind, right? And the crazy part is, almost all of these decisions about exactly where to look next happen entirely without our conscious awareness. It's a continuous, subconscious loop of perceptual processing and motor commands, just firing off constantly as we navigate the world and soak up information. To really understand how we read, we have to look at the anatomy of these movements. Remember how I said reading isn't a smooth video pan? It's actually much more like taking rapid-fire snapshots with a camera. Your eyes are completely still for these really brief periods called fixations, which last a tiny fraction of a second, about 150 to 400 milliseconds. This is literally the only time your eye is actually absorbing visual information from the text. And these static snapshots, they're separated by extremely rapid ballistic jumps called saccades, taking just 20 to 35 milliseconds. During a saccade, you're essentially blind. You see absolutely nothing. Foundational research in eye tracking actually shows that our eyes are jumping forward in tiny, distinct chunks. We're talking about 7 to 9 character spaces at a single time. So why do we do this? Well, it's because of the physical limits of our own vision. High-resolution vision, the exact kind you need to identify small, intricate shapes like letters, is limited to the fovea, which is the very center of your retina. As your eyes jump, they're desperately trying to place the next crucial chunk of text directly into that tiny, high-acuity foveal zone. It's like constantly trying to keep a spotlight right on the most important words. But here is a truly shocking statistic for you. We don't just march relentlessly forward when we read. Up to 15% of our saccadic movements are actually what we call regressions. That means 10 to 15% of the time, your eyes are darting backward to text you've already read. You are constantly double-checking yourself, fixing overshoot errors and rereading. And the wild part, you're doing all this mostly without even noticing it's happening.
Let's move into Section 1, Zooming In, the micro world of reading.
So even during a fixation, when you think your gaze is perfectly locked onto a single word, your eye is not actually resting. Not at all. It's twitching violently at a microscopic level. We call these microsaccades. They are tiny, involuntary, jerk-like jumps measuring less than 1 degree of visual angle, and they're happening 1 to 3 times every single second. Historically, scientists just dismiss these as random oculomotor noise, but high-precision tracking reveals they serve a profoundly important biological purpose. The crucial point here is absolutely fascinating. If your eye didn't constantly do this twitching, your vision would literally stop working. Constant focus on a static image causes neural adaptation in our eyes. Basically, the image would just fade away into a blur. It's a phenomenon known as Troxler fading. By continuously shifting the retinal image by just a fraction of a millimeter, these microsaccades stimulate adjacent photoreceptors. That defeats the fading and keeps the fine details in the letters you're looking at perfectly visible. But during reading, these twitches do way more than just keep the lights on in your brain. When we break down the different types of reading microsaccades, we see that over half of them, 53%, are what's called intra-word corrective, meaning when your eye makes a big jump to a really long word and accidentally overshoots the best viewing position, your brain frantically uses a microsaccade to pull the text a few characters backward, yanking it right back into that optimal high-acuity zone. Another 23% are exploratory twitches, quickly checking adjacent short words to resolve confusing meanings without having to commit to a major backward jump. It's incredibly efficient. All right, Section 2, the mechanics of comprehension, how the brain calculates text on the fly. Your brain is basically performing these incredibly complex, high-speed calculations on the fly to figure out exactly where to look next, and it relies on 3 major variables. The primary cue is word length. We skip short words constantly, while long words almost always demand a direct fixation. Next up is word frequency.
Common everyday words get much shorter looks than rare ones. Finally, we have predictability. If the context of a sentence makes the next word super obvious, your brain might literally just skip it entirely to save time. It's this highly efficient system that skips what's easy and slams on the brakes for what's complex.
You can clearly see how heavily text difficulty influences this whole process. When you hit a structurally difficult sentence, maybe something that's written in a confusing way, or when a specific word completely shatters what you thought the sentence meant, your eyes instantly trigger a regression. They literally dart backward to the exact point of confusion to reprocess it. So when comprehension fails, it's a massive driver of these regressive eye movements. Which brings us to Section 3, the modern battle: paper versus digital screens. For a long time, there's been this debate about reading on a screen versus reading a physical book. Well, we have some incredible data from a University of Oslo eye tracking study that really puts it into perspective. Researchers took 10 8th grade students with varying reading levels and tracked over 25,000 individual eye fixations as they read comparable text on paper and then again on a digital screen. This gives us this perfect, direct window into how the medium we are holding actually alters our biological reading process. The contrast between the two is honestly stark. When reading on paper, these readers developed deep comprehension and structural retention. A physical book gives the brain these tactile, spatial cues that actually help build an organized mental map of the information. But on a digital screen, those physical cues just disappear. This lack of a spatial map disrupts your eye movements, triggering fragmented saccades, highly inefficient rereading patterns, and just excessive skimming. The ultimate result is significantly shallower processing of the information. And here is probably the most concerning finding from the entire study. The students had absolutely zero metacognitive awareness that their behavior had even changed. They didn't realize the screen was fundamentally altering their eye mechanics and impairing their comprehension because all these changes are happening at this microscopic, subconscious level of saccades and fixations. We just naturally assume we're reading exactly the same way no matter what device we're holding.
So, what do we do about this? Section 4. Strategies for better reading. Taking back control of your eyes.
Depending on your actual goal for reading, your eyes actually need an entirely different strategy, and thankfully, our eye movements are highly adaptable. Normal reading hovers around 200 to 300 words per minute with standard baseline regressions. But watch what happens when you switch to thorough study mode to maximize comprehension. Your speed slows down, your saccades become shorter and much more controlled, and your regression frequency actually increases as you constantly loop back to encode those memories. On the flip side, skimming relies on these long, wide jumps and tries to minimize regressions entirely, which, as you can guess, directly impairs your ability to retain the details. Since you don't naturally realize you're slipping into the skimming mode on a digital device, you actually have to actively force your eyes to perform deep reading mechanics. Think of this as your digital reading survival guide. First, consciously slow down your pacing. This forces your eyes to make shorter, more controlled saccades. Second, actively take notes while you read. This helps create that structural and spatial map that digital screens are missing. And third, pause and reflect on the text. This manually triggers the regressions that your brain would normally be doing automatically if you were holding a physical book. So, to wrap this all up, our eyes are performing this incredibly complex, high-speed ballet of stops, jumps, and microscopic twitches every single second that we read. They're constantly adapting to the difficulty of the text, and they adapt, sometimes pretty poorly, to the modern screens we stare at all day. So I want to leave you with a thought. The next time you pick up your phone or tablet to read a long article, try to watch your own eyes. Are you taking the time to truly read and comprehend, or is the screen hijacking your oculomotor system and just letting your brain skim the surface? Seriously, think about that the next time you swipe open your device.